This video is about section 4.2 in the Blitzer Precalculus book. Let's start off with a point that's on the unit circle. I'll take any one of them here, and I think in particular I'm going to take this point, and that's for negative square root of 3 over 2 and 1/2 for the x and the y. That happens to make it at 150 degrees, or 5 pi over 6. But what we're interested in is the fact that that's the x value and that's the y value for this point P. So that tells us certain things. That tells us what the sine of P is, or the angle here, this angle theta. The sine of theta, or 150 degrees, or 5 pi over 6 in this case, the sine is 1/2. The cosine is automatically that x value, negative square root of 3 over 2. And from those we can derive the other four. So we're going to derive the tangent, we're going to derive the cosecant, put theta there, we're going to derive the secant of theta and the cotangent of theta. So in this case we're also going to combine here with what example 5 is. I think it's example 5 in the book too. Example what is it? 1 has some of this, and we'll be doing a good deal more of these where you have to do various parts of them. And I think we're going to focus one of these on the test. I think you'll see some form of this, so be ready and prepared for that. Cosecant is nothing more than the reciprocal of this, or actually you can think of it as 1 over sine theta. Well, 1 over sine theta would be 1 over 1/2 multiplied by 2 over 2, and you would get 2 over 1, or 2. So the cosecant of theta is 2. Okay, let's do my work over in this spot. The secant of theta would be 1 over negative root 3 over 2. Or if, and then, well, actually let's do this the long hard way first. And I multiply by 2 over 2, and I end up with negative 2 over root 3, and you have to rationalize that. So when I multiply by square root of 3 over the square root of 3, I get negative 2 root 3 over 3. Well, now, if I just simply switched that and did negative 2 root 3, I would get over to this spot immediately without having to do 1 over square root of 3 root 2 negative. So in any case we now get negative 2 root 3 over 3. Down here for the tangent is the same as the y over the x, which means it's the cosine over the, oops, no, I had it right when I started writing sine first. It's the sine over the cosine. This is called one of the quotient properties, and then you do the same thing with cotangent. Cotangent, though, instead of being sine over cosine, is cosine over sine. Again, like the reciprocal of this one. So the cosecant matches the sine as its reciprocal, or 1 over the sine of theta. Okay, that's a reciprocal property. Reciprocal property, and then this has the reciprocal property of 1 over cosine theta, and these have what's called the quotient properties. I don't care you remember the names of them, just that you can use them. So if that's going to be y over x, that's going to be 1/2 over negative root 3 over 2. Well, we're going to have to work that out by multiplying on top and bottom by 2 over 2. And we'll get negative 1 over root 3. So once again, we have to multiply by root 3 over 3, negative root 3 over 3. So I'll put negative root 3 over 3. So that's the tangent of theta. Cotangent theta, well, we have two choices. We can figure that out as cosine over sine, which is x over y. And so I could do negative root 3 over 2 divided by 1/2. I can also go back to one of these spots with the tangent and I can switch it. Just do the reciprocal of this, and I'm going to get negative root 3 over 1, which is just negative root 3. If I did do it as x over y, I would have had negative root 3 over 2 over 1/2 multiplied by 2 over 2, and the 2's cancel, and I get negative root 3. Geez, just as easy. So I get this one, and this one, and this one, and this one. These two, because they're given as the point. And then these 4 by deriving them. And that's one of the things you will have to be ready to do, no matter what the points are. Notice it doesn't matter that they are a specific 30 degree, 45 degree, or 120 degree, or their matching counterparts. It can be any x or y point, and you can derive the sine and cosine from them if it's on the unit circle. If it's not on the unit circle, there'll be a way you'll learn that in another section, or if you remember from last year, where you did it, where you'd have to use the radius as well. Here we don't have to use the radius because its radius is 1 already. Now, next thing I want to talk about, we'll call that like part 1 of this. Okay. And, let's see. Let's do the same thing here with one of the quadrantal angles. The quadrantal angles are the basic 90, 180, 270, and 0 or 360 degrees. And these have the much simpler 0 and 1, 1 and 0, negative 1, 0, and so on. Let's take 270 degrees, where the x is 0 and the y is negative 1. Sine of 270, cosine of 270, tangent of 270, and then we'll do the cosecant of 270, the secant of 270, and the cotangent of 270 degrees. Alright, well, these first two are easy. The cosine is going to be at negative 1, and the cosine of 270 degrees is 0. Well, the tangent is the sine over the cosine, and that's negative 1 over 0, which is not possible, so you actually say undefined. The cotangent, though, that one's going to be the cosine over the sine, and that's 0 over negative 1, which is simply 0, so it is indeed a good number. The cosecant of 270 is going to be negative, instead of negative 1 over 1, we'll do 1 over negative 1, which is still negative 1. That doesn't change. But for the secant now, this one was 0 over 1. When you reverse it, you get 1 over 0, which is not allowed, so it's undefined. So we have two of them that are undefined, and then the other ones are, perfectly fine here. Normal negative 1s and 0s based upon which of the trig functions they are. So that's our second thing. Now, let's talk about the third one here briefly. The third one about even and odd functions. So for even and odd functions, the basic rules are this. If you take negative theta, the negative angle for sine, you end up doing negative the amount of sine of theta, whatever the actual amount was in the first place. For cosine negative theta, that doesn't change at all. You end up with the same cosine of the original angle instead of the negative of the angle. Well, it is the same. The tangent of negative of the angle is the same like the sine. It's negative in front. It's like that negative goes in front. Here's why. Let's take a look here at a unit circle and at 45 degrees. So at 45 degrees we have root 2 over 2 and root 2 over 2. Well, let's come down here to this one. Let's take the negative 45. This is 45. Negative 45 just means going this way, so that's negative 45 degrees. Well, the sine at negative 45 degrees, since all in the fourth quadrant is negative, it is indeed the negative of what the sine of theta is. But the cosine is the same. Notice that in the fourth quadrant, all the cosines are positive. That's why that one stays positive. And since the tangent is nothing more than the sine over the cosine, you're going to end up with a negative. Here, sine over cosine is a positive 1. Here, sine over cosine is a negative 1, which is the negative of that positive 1. So that explains the even and odd functions. You don't see them that often, honestly, but now you recognize the point of them and why it works that way. So if you were to see it at any point, it should make sense just what it's all about. Now we want to talk about something from example 6. In particular, Pythagorean identities. Pythagorean identity. The main Pythagorean identity. That's the first one we're working with in this section. We'll get into more later, I think, in the next chapter. And you should remember this one from last year. I didn't make you memorize all of these, but this one you do have to memorize. And it's the sine squared theta plus cosine squared theta is equal to 1. And yes, that should be written as sine theta squared. That's the real way that that should be written, and even mathematicians agree with that, except this has become so much convention in math that everyone does it, and we're sort of stuck with it. So, let's check something out. Let's check 60 degrees out. At 60 degrees on the unit circle, the cosine is 1/2 and the sine is square root of 3 over 2. Does this work to say that the cosine squared plus the cosine, sine squared plus cosine squared really equals 1? Is that actually true for the points? Well, watch what happens. The sine of theta is the square root of 3 over 2. We're going to square it. And the cosine of theta is 1/2, and we're going to square it. And is that really equal to 1? Well, square root 3 and you get a 3, square 2 and you get a 4. So you get 3/4 from that. When you square 1/2, you get 1/4, and 3/4 plus 1/4 is indeed equal to 1. Checks. If you want to try it with other numbers, feel free to go right ahead, and you're going to find it works every time. I was going to do it with 45, but I don't think we need to. Okay. Now, let's talk about a slightly different type of thing. Based on this rule, we're going to be able to use it to find out other parts or other things. Like if I don't know sine, I can still find out what cosine is. And here's how it works. This one is like example 6 in particular. Like example 6 down here. Okay. So, given that the sine of an angle, they call it t in the book, I don't know why, but we'll use it, is equal to 7 over 8. And with this qualifier, that 0 is less than or equal to t, which is less than or equal to pi over 2, that's 90 degrees. So what that means is we're talking about this area here, so that means we're only dealing with the first quadrant. That's an important thing for the end of it, especially at the end of it. So we're going to use the Pythagorean theorem, sine squared theta plus cosine squared theta is equal to 1. Because that's going to be enough. If we know the sine on the unit circle, we can use that to get the cosine, or vice versa. But we also need a qualifier because we're going to end up with two answers at first. We'll put 7 over 8 in here and square it. At this point, it just becomes normal algebra that you have done before. Now subtract the 49 of 64th from both sides. Minus 49 over 64. But here you have to remember basic fractions where you're going to have to change this into 64 over 64 minus 49 over 64. So this was subtracted out, so we have cosine squared of theta equals 1 minus that, or 1 minus that. 64 take away 49 is 15 over 64. And now, since in reality that's really cosine theta squared, we can take the square root of both sides. So if I take the square root of this side, I get cosine of theta. If I take the square root of the other side, I get plus or minus the square root of 15. Square root of 64 is 8. So I now have a number for the cosine, but I have two of them. However, the cosine is positive only in the first and fourth quadrants. It's negative over here, and it's negative down here. So square root of 15 over 8 is actually in 4 different places, but in these two it's negative. And in the two that it's positive, only one of them is in the first quadrant. So because of this qualifier, that means the only answer is the positive one of it. So I'll cross out the negative, and I'll say cosine of theta is equal to square root of 15 over 8. Now think about something. If over here I had done pi over 2 less than or equal to t, less than or equal to pi, that would have told you it was between 90 and 180, and it would have been over here. And if that had been that qualifier, then down here I would have chosen the negative, not the positive, to be the answer. So be aware of that and pay attention to that kind of little detail, and you won't have a problem picking the correct one of that type of for that type of problem. Now, one more of these I want to point out. No, let's see, do I want, oh yes. The next part is also really simple in terms of concept, and it's really just multiple versions of the same angle. So also in 4.2, and I guess this will be like example 7. So if we are on the unit circle and we're at pi over 4, if we go around one more time, well, first, right now we know that's square root of 2 over 2 and square root of 2 over 2. If we go around again, all the way around, we end up back here, and it's still the same sine and cosine. Those don't change. So if I say, ask for the cosine of pi over 4, or the cosine of 45 degrees, that's what's it, square root of 2 over 2. Square root of 2 over 2. If I go around one more time, whatever that cosine is still, or whatever that angle is still square root of 2 over 2. I want to find that angle. If I go around once, I have to add one revolution. And think about the fact that on the unit circle, when you're here at 360 degrees, that's 2 pi. Well, it was 1 pi here, and it's 2 pi to get over here because we're going on this outside movement. So we end up back here, so it's 2 pi is one time around. Therefore, if I start here and go around, it's still 2 pi. All I really have to do with pi over 4 is I have to add 2 pi to it. And that's what the angle is that's gone around an extra time. But we can't write it as 2 pi over 4. We're going to have to write it over 4. So that means it has to be 8 pi over 4. So that's 9 pi over 4. So since 2 pi is the same as 8 pi over 4, we can do this all day. We can add another 8 pi to it. We're going to get 17 pi over 4, and that's also equal to square root of 2. And another 8 pi over 4 would give me 25 pi over 4, and so on, and so on, and so on. And you can go in reverse. If I subtract 8 pi over 4, I'm going to get, I think, negative 7 pi over 4. And that's what this is. If I started here and I went around this way, it would be negative. So that means cosine negative 7 pi over 4 is also equal to square root of 2. Okay. Well, that's all there is to it. No matter which angle it was, it would be pi over 3, and you just add 6 pi over 3 every time, or it could be 180, it could be pi, and if you added 2 pi, you'd be at 3 pi, and another 2 pi, and you'd be at 5 pi. So every place on the unit circle, that's all you'd have to do, would be just to add 2 pi in order to get to another version of the same angle. Okay.